Algebra 2, target 27. I can solve exponential and logarithmic equations. Today our focus is going to be on solving exponential equations. And we're going to solve two types of exponential equations. One type is going to be when we have an exponent equal to an exponent. A to the x equals b to the x. And the other type is when we're going to have an exponent equal to number. A to the x equals c. So let's take a look at those two types. The first type we're going to look at an exponent equal to an exponent. Basically our theorem is if we have b to the x equals b to the y, the bases are the same. If the bases are the same in order for the exponents, in order for the equation to be true, so must the exponents. So if b to the x equals b to the y, since the bases are the same, x must equal y. Or in this case, 3 to the x equals 3 to the fifth, therefore x equals 5. So let's try that a couple times. Solve 4 to the x equals 1/2 to the x minus 3. The problem we have here is our bases aren't the same, so we need to rewrite the bases. Now, if you look at 4 and 1/2, they have 2 in common. So what we're going to do is we're going to rewrite 4 as 2 to the second. So 4 is 2 squared, so we're going to have 2 squared to the x. And if you remember what you had for exponent rules with fractions, those are negative exponents. So 1/2, that's the same as 2 to the negative 1. So we're going to write the right side as 2 to the negative 1 to the x minus 3. And now we want to simplify. Here, power to a power, you're going to multiply. So that becomes 2 to the 2x. Here, power to a power, again, so we're going to multiply. We need to remember to multiply negative 1 times the entire expression here. So we need to group it, and that means we're going to distribute. So that rewrites to 2 to the negative x plus 3. Now we have exponents with the same base. Therefore, the powers must be the same. So we can rewrite this as 2x equals negative x plus 3. And now it's a linear equation. We can solve it like we solve a linear. Add x to both sides. 3x equals 3. And divide by 3. X equals 1. As always, we should check it. So we will take and plug 1 in. 4 to the first is 4. 1/2. Make sure you group your 1/2 to the 1 minus 3 is 4 as well. So it checks out. Let's look at another one. What's the hidden base here? We got 9 and 27 are bases. Those are both powers of 3. 9 is the same as 3 squared, so we're going to rewrite 9 as 3 squared, and then 2 to the 2x. 27 is the same as 3 cubed, so we're going to write this right side as 3 cubed to the x minus 1. Now we want to simplify. Power to a power will multiply, so that would be 3 to the 4x. And then here, 3 times x minus 1, remember to group so that we can distribute. We got 3 to the 3x minus 3. And now we're back where our bases are the same. Therefore, our exponents should be the same. So we rewrite this as 4x equals 3x minus 3. And we'll solve it as a linear equation. Subtract 3x from both sides. X equals negative 3. And then let's check our work. All right, so we got 9 to the 2 times negative 3. We got 1.8 times 10 to the negative 6. Check the right side, 27 to the negative 3 minus 1. And we got 1.8 times 10 to the negative 6. They are the same. Try this one on your own. Pause it. We'll come back. 100 is the same as 10 squared. So I'm going to rewrite this as 10 squared to the 7x plus 1. And 1,000 is the same as 10 cubed. So we're going to rewrite this as 10 cubed to the 3x minus 2. Now remember, when we simplify, we want to multiply, but remember to group it so that we can distribute the 2. So this becomes 10 to the 2 times 7x is 14x plus 2 equals, distribute here, we got 10 to the 9x minus 6. And again, our bases are the same. Therefore, so must the exponents be the same. So we can rewrite this as 14x plus 2 equals 9x minus 6. Then solve it like you would any linear equation. Subtract 9x from both sides. We got 5x plus 2 equals negative 6. Subtract 2, we got 5x equals negative 8. Divide by 5, x equals negative 8/5, or you can say negative 1.6. Let's do our check here. 100 to the 7 times negative 8/5 plus 1 equals 3.98 times 10 to the negative 21. 1,000 to the 3 times negative 8/5. Whoops. 1,000 to the 3 times negative 8/5 minus 2. They equal the same thing. Good. All right, so let's move on. Now let's talk about logarithms. All right? Remember, a logarithm is the opposite of the exponent. So saying b to the x equals y, that's the same thing as saying log of y with the base b equals x. So if we have an expression like this where it's an exponent equal a number, we can convert it to a log and solve it that way. So let's take a look at our first example here. 4 to the x equals 11. Let's rewrite that because it's an exponent equals a number. Let's rewrite that as a log. Right? So we're going to do log base 4 of 11 equals x. Basically, the x and the 11 switch places when you convert it to a log. And if you remember our change of base formulas, because your calculator doesn't do log base 4, x equals log 11 divided by log 4, which is approximately log 11 divided by log 4, approximately 1.73. Right? Same thing here. We have an exponent equals a number. So rewrite that as a log. The base of our log should be 2. The 5 and the x will kind of switch places. So it'll be log base 2 of 5 equals x. And then we'll use our change of base. I'm going to use the natural log this time. Remember, it doesn't matter if you use natural log or the common log as long as you're using the same in the top and bottom. So x equals natural log of 5 divided by the natural log of 2. And we got approximately 2.3. And of course, we should check. We didn't check the last one. 2 to the 2.3219. It doesn't equal exactly 5 because we rounded, but you can see it's pretty close. All right, try this one on your own. Pause, try this on your own, we'll go through it together. So here we have an exponent equal to a number. The exponent's a little different in the fact that it's not just x. Treat it the same way you would as if it was just x. In other words, we're going to rewrite it as a log. Log base 7 of 15 equals 9x. And how do you get rid of the 9? Well, we'll divide both sides by 9. So we got x equals log 15 with a base of 7 divided by 9. We can estimate that natural log of 15 divided by the natural log of 7, and then divide that by 9. 0.154. Do a quick check. 7 to the 9 times 0.1546 should be pretty close to 15. And it is. The more places you're going to carry it to, the closer you'll get. Let's try this one. A couple differences here. We got this subtracting 7 out in the back that the other ones haven't had. And we got this 4 that's multiplied by the base that we haven't had before. It's no secret. You're just going to treat it like it's linear until you get it to the exponent by itself. So the first thing you're going to want to do is you isolate your exponent. So we will add 7. So 4e to the negative 0.3x equals 20. We'll divide by 4. E to the negative 0.3x equals 5. And now we have an exponent equal number. We'll convert it to a log. This is a special case, though, because our log has a base of e. So we can use a natural log. So the natural log of 5 equals negative 0.3x. Divide by negative 0.3. And x equals natural log of 5 divided by negative 0.3, which we can estimate out to be remember to close your logs, or otherwise there's going to be mistakes. Negative 5.36. All right, so in conclusion, you're going to have two ways you're going to see these exponent problems. You're going to have an exponent equal to an exponent. If that's the case, you want to get the bases to be the same, and then you can set the exponents equal to each other. Or you're going to have an exponent equal to a number, and if that's the case, you want to convert to a log. Always make sure if there's extra stuff, you isolate your exponent first. And then you do your logarithm.